Yes, Doctor.
Yeah, please uh, make it in presentation mode, you know.
yeah,
I think,
sure.
yeah. Yes, please.
Yeah, good afternoon, Prof. Musa and all of my colleagues. My project is a techno-economical reliability informed evaluation of strategic transition from capital expenditure to operational expenditure in health technology management. In this project, I studied how hospital can evaluate different procurement models for, as you know, medical equipment, not only from financial perspective, but
Hmm.
also from reliability and operation perspective. Okay, so healthcare technology management now as a strategic function in hospital, and the budget of medical devices was almost a 10%, from 5 to 10% of the hospital total budget. So it's huge, and it must be a strategic function in the hospital. Medical equipment such as MRI, magnetic resonance imaging, also CT and linear accelerator are essential for diagnostic and treatment of the patients. So the procurement decision is important because it affects the hospital for many years, and also affects the budget, maintenance responsibility, equipment uptime, and service continuity. Also, it will affect the patient satisfaction. So the main motivation in this project, that many hospitals still evaluate procurement of the medical devices mainly from the cost side, while the cost and reliability should be evaluated together. So the main problem is that procurement is often treated as a budgeting problem only, but in reality, it's also a reliability problem. For example, in my case study, I took an MRI machine as a, uh, I'd say, a pilot, so I can. Usually, the MRI system or machine under the traditional ownership, which is CAPEX, that my experience around 290 hours of downtime per year. So this lead us to cancel appointments, diagnostic backlog, reduce also the satisfaction of the patient, and increase the queue or the uh, patient appointments. So the question is not only which model cost less. In my opinion, the real question should be which model gives the best balance between cost, availability, and service performance. In this slide, as you can see, the comparison of two main procurement architectures. In the your left hand, the capital expenditure, which is CapEx, means the hospital buys and owns the equipment. The hospital pays the acquisition cost at the beginning and keeps full responsibility, maintenance, upgrading, and take the whole risk. On the other hand, the operational expenditure, which is OPEX, means the hospital pays for access and availability or usage of instead of full ownership. In this model, some of the maintenance responsibility is transferred to the vendor or the supplier. In my project, I studied three operational expenditure variants, which are leasing and managed equipment services, which is MES, and pay per use. So the core difference is CapEx is ownership based, while the OpEx is service based. Uh, the literature shows three important gaps. First of all, the financial analysis and reliability analysis are usually studied separately. The second thing, MAS, which is Managed Equipment Services, are often discussed qualitatively, but not always evaluated numerically. The third one, the cost of, and availability and decision-making logic are rarely integrated into one framework. So in this study, I tried to fill the gap between the decision by combining life cycle cost, equipment availability, and multi-criteria decision logic and sensitivity analysis. So the contribution is integration, not just another cost compression. And this project has four main objectives. First one, to build a net present value, uh, which life cycle cost model for ownership and service-based procurement. The second one, to build the reliability-based availability model linked to repair time. The third one, to combine cost, availability, and maintenance burden into one decision score. Finally, to apply a framework to MRI machine case, which is my case study to test sensitivity and of the result. So the project has both analytical and applied analysis. The methodology here, first one, I defined the case study, which is MRI machine. Then second one, I calculated life cycle cost using net present value. Then I calculated availability using simplified Markov two-status approach. Fourth, I scored the scenario using a weight multi-objective method. Finally, I performed sensitive analysis to test how robust in conclusion are. All of this was implemented in reproducible Excel workbook so the model can be checked and updated easily. Okay, here is the main cost equation used in my project, which is NCC is life cycle cost is calculated as a sum of all year cash outflows discounted to present value using discount rate, which is R here. So LCC, as I said, life cycle cost mean the total cost over the planning horizon. The C sub T is cash outflow in year, means the cost paid in a specific year. Let's say the second year or the third year, for example. The R here is discount rate, which is annual discount rate, which here in my study, 5% in this in my study. The N is planning horizon, which is 5 years. The important points here, the downtime cost included in all four scenarios. So it would make my study fair. Here, to present reliability in a simple and useful way, assume the equipment has only two status, which is working and under repair. Then I calculated the availability, which is A, using the equation as you can see. The mean time between failure, which is MTBF, divided by mean time between failure, MTBF, plus mean time to be repaired. What does that mean? So here, the mean time between failure means how long equipment operates before the failure happens. And the mean time to repair means how long take how long it take to restore the equipment after failure. So the key idea in this study is that the procurement strategy main affects mean time to repair, not mean time between failure. In other words, the contract change how fast we can fix the equipment, not how quality the hardware itself. So for the case study, I selected MRI machine. I chose this technology because it's high value, maintenance intensive, and very sensitive to downtime. The planning horizon here is 5 years. The main time between failure is kept constant at 4,000 hours because it's treated as a hardware property. The annual operating time is average 3,650 hours, and discounted rate is 5%. Then I compare for a scenario. The C1 is CAPEX ownership, C2 is leasing, C3 is managed equipment services (MAS), and C4 pay per use. The main difference between them is the main time to repair and the cost structure. And this slide shows the 5 years life cycle cost result. The result are leasing has 11.3 million real, and pay per use has 11.65 million. Managed equipment services 11.95, and capex 13.46 million. The most important finding here in this slide, the capex is actually the most expensive option when downtime and discounted cash flow is or are included. This mainly because the large year zero acquisition cost, which is here 6.5 million, in addition to highest downtime burden. This slide presents the operational side of result. Managed equipment services achieve the highest availability around 97.3%, while the capex around 92%. In terms of downtimes, in the right of the slide, the capex gives about 294 hours per year. The MES managed equipment services gives about 98 hours per year. That means when we are moving from capex to MES managed equipment services, reduce annual downtime by about 67%. Operationally, this is very important because it means usable clinic time and better service continuity, the patient satisfaction, etc. After that, I did, as you can see in this slide, I did the multi-criteria decision-making conversion. I combined three objectives: minimize life cycle cost, maximize availability, and minimize maintenance burden. Then I tested the three weights scenario, which is, as you can see here, sorry. Okay, as you can see here, the cost priority, availability priority, and balance priority. The result is under the cost priority, pay per use is preferred option. Also, under the balanced weight, managed equipment services (MES) is still preferred option. So the key here is that there is no universal winner, but Cabex almost is not the preferred option in the tested weight scenarios. As you can see here, I tested each scenario against five constraints, which are budget, availability, SLA, surface level agreement, response time, government complexity, and operational readiness. The important result is that the CAPEX fails to constrain the SLA response time, operational readiness. Also, the OpEx scenario passes all the constraint. So under the baseline assumption, the CAPEX is not only weaker in ranking, but also infeasible in this configuration. Okay, in this slide, because the result depend on almost, it's not a real data, but it's assumption of I tested the sensitivity. The most important sensitivity variable was annual scan volume because per use depends on directly on usage. This mean break-even points are around 1,740 scan per use versus lasing around 1086 scans per use versus managed equipment services, around 12,150 scans per use versus CAPEX. This means pay per use is attractive mainly when annual demand is low or variable. But when scan volume becomes high and fixed fee models or ownership become competitive, so it's give very practical decision rule for any hospital. And to conclude, there are four main findings from or for this project. First one, the CAPEX was the most expensive option after including downtime and discounted cash flow among the 5 years. The second one, managed equipment services achieved the highest availability. Third one, per use is only attractive below certain annual scan volume threshold. The fourth, CAPEX failed to practically constrain in baseline case. The broader conclusion is the procurement should not be treated as a budgeting choice. It should, in my opinion, it should be treated as a reliability informed engineering decision. The fixed cost and downtime and long term hospital performance, it will be also affected. So that's all. Thank you, Prof, and thank you all. If there are any question, I'm almost done.
Thank
Shukran.
you so much. Very interesting and very good presentation. It was it has a very strong structure. So thank you so much for your presentation. We have to hurry up a little. So who is the next person? Thank you, Mr. Turkey. Please upload the last version of PowerPoint in the Blackboard. So this weekend I want to review all of the PowerPoint presentation and everything. So please make sure that everybody already upload the PowerPoint in Blackboard before Friday, please. Yes.
If possible, I can present, Doctor.
Sorry? Yes, please. Yes, please.
If possible.
Yes, yes, please, please. Share your screen. As I mentioned, I'm recording the presentation and I will upload the video in my YouTube channel. So if you have any problem or issue, please let me know. So, and one before your presentation, Mr. Fad, regarding the your exam, final exam, only 8 students attend to the vote. So could you please let me know why what about other students? Totally, I think I have 15 students should be in the class, right? Mr. Abdulaziz, are you here?
Yes, yes.
Assalamu alaikum, Mr. Abdulaziz.
Alaikum salam wa rahmatullah.
Yes, only 8 students participated in in your vote. So what happened? What about the other students?
I think some of them they have some difficulty to attend to attend the exam in that date,
Oh, okay.
and then the last lecture I think you have like a proposal or suggestion to be
Yeah,
discussed in this lecture.
yeah.
So that's why some of them they didn't participate.
Okay.
They are thinking like to propose another date or something.
So what about 20? I'm okay with 20 or Tuesday, 2nd of June. Uh,
Yes, I can post the vote for the new dates and
yes,
let's
please.
see like.
Maximum 2nd
So,
of
so what
June
is
is okay.
so second of June and
Prof, can
there
we
is
20.
do
another
it
date.
online, Prof?
No, no, no. It should be in
As you
person.
know, it's before a Hajj, so
No, no,
it's
no, no.
difficult to
The
find a
final
place.
exam should be in person. We cannot do online. I just prepare the online session because I want to have most of you in the class. That's why this is my reason, and everybody can attend to the other students' presentation. It can help them a lot to increase the quality of their presentation itself. So that's why I ask if we can have online presentation. Otherwise, I'm here. So for me, it doesn't matter. I can be in person, physically in the class. So, but regarding the final exam, we cannot do online. It should be in person based on the
Okay,
regulations. So,
so you proposed second of June and there is
or
another date or
20 of June also is okay. Wednesday before vacation.
2 of
Wednesday.
June and 20 of June,
20 of May.
right?
20 of
20
May.
of May. Okay,
Yeah, yes.
okay, okay,
2nd of June
okay. I
or
will.
3rd of June, but 2nd of June and 3rd of June, I have other final exams. So please let me know at what time. For example, in the morning, it can be very good. Um, and yes, please let me know in advance, please. Yes, please make another vote.
Okay, for
Even
we have now 3 days.
yes,
Uh,
even next
second of June.
Monday. Yes, yeah, even next Monday, 18th of May. After presentation, it will be very late. For example, at 6:30 up to 8:30, if all of you are available, I am okay. From my side is okay. So could you please, Mr. Abdulaziz, make
Yes.
suggest 3 times, 18th of
Okay.
May at
Okay.
after class. So after 6:30 up to 8:30, for example, or Tuesday, 19th of May, 20th of May, at any time, and also 2nd of June and 3rd of June. At in
Okay.
the morning is okay, is better, or in the afternoon. Please let me know. And
Okay.
because at this moment is not clear, other final exam. Uh, Two of my courses are will be in 2nd and 3rd of June, but I'm not sure about the time, at this moment.
Okay. I will post the vote in the
Yeah,
WhatsApp.
yes. The maximum
Okay.
should
Thank
be 3rd of June. After that is very difficult. So
you. Okay. Okay.
Yeah, because if it can be before the vacation, it can be very so better because I can review all of your final exam better and very fast. Yeah, because I'm here. I don't have any other um, things to do, so I can take time to review your exam. All right?
Perfect.
Yes,
Perfect.
thank you so much. So, Mr.
You're
Faz,
welcome.
sorry to interrupt you. Please start your presentation.
That's okay. No need to mention. Assalamu alaikum warahmatullahi wabarakatuh.
Salam alaikum.
Uh, this is Fahd Al-Qahtani. I am glad today to present one of the most important topics among power grids business. My topic is related to reliable reliability analysis of telecommunication networks in power grids
Yeah.
using probabilistic methods, risk assessment, and Monte Carlo simulation. In this presentation, we will be having 14 items as an outline. The first one will be, inshallah, having introduction and operation context. And then we will be talking about literature review and research gaps and gap analysis. And then we will be talking about methodology that we used in this project. Also, we will be talking about mathematical model and system modeling using reliability block diagram, and also we'll be talking about real data analysis in 2025. Also, we will be presenting KPIs calculation, and then we will be having the Monte Carlo simulation. Also, we will discuss the 2026 improvement and enhancement. And then, inshallah, we will be talking about course industry integration and discussion, and then conclusion, recommendations, and the reference. To introduce this project, we will be talking or maybe asking a question: why telecom reliability matters in power grids? In power grids, it's very essential to be monitored and controlled. Without this kind of controlling and monitoring the whole network, the reliability of power grid cannot be measured and cannot be done. Through telecom layer, we'll be having many different technologies. We will only talk about some of them, such as MPLS-TB, IP-MPLS transport, and DWDM fiber optic backbones, and SDH and TDM networks, and then LAN WAN data networks, and DC power supply systems specialized for telecom and SCADA, and also we will be talking about data centers and application. Also, we will be talking about in our systems, we used to have power grid control using RTUs and SCADA, elementary and remote controls, substation automation, which is nowadays is the most advanced system. Also, we are having protection relay signaling and real-time grid monitoring. Also the failure impact is actually having a lot of loss of supervisory feasibility, preventing control from controlling and monitoring, and delay control actions, and extended outage restoration, and cascading grid instability. Failure in communication network translate directly in loss of control over the power infrastructure. In 2025, we had over 107 faults. These real data actually in this project, I intended to integrate what we have learned in this valuable course with the real case study and real industry and business. And this is why we brought all these kind of figures and numbers. Back to the incidents in 2025, we had more than 25 incidents, and the frequency of events per day is 1 to 2 events per day. The literature review in reliability assessment methods, we have 4 methods and distribution models. The first one, analytical model, which using exponential and log normal distribution, and the TTF, the time to failure, which provide mathematical closed form solution for system performance. The strength of this method is fast, transparent, and computationally efficient. The limitation is it assumes constant failure rates, complex for non-Markovian states. In the second method, the RBD, which is the reliability block diagram, using the series and parallel and the high part configuration, which identifies SPOF, single point of failures, and the impacts of redundancy related to the standard of IEC 61078. The strength of this is visual, modular, and identifies the redundancy gain. But the limitation is limited to statistic topologies and difficult for multi-stage systems. The FME, which is the failure mode and effective analysis, and also the FTA, which is the fault tree analysis. This is the third method that we use, which is from bottom up. The FME-A on the top down, which is the FTA, inductive and deductive logic maps failures. It usually maps failures, modes, and root causes, and critical paths. The strength of this method is high root cause clarity and risk identification. But it also has a limitation, which is partially qualitative and requires extensive expert judgment. And the last method we used, which was the Monte Carlo simulation, stochastic random sampling. We use about 5,000 trails, evaluating complex network reliability by simulating failures per repair events. The strength is handling the uncertainty and complex topologies. The limitation of this method is high computational cost, and results are statistical estimates. The gap analysis in this project was answering the question, which was what is the missing in the existing approach. The first gap was the integration between telecom and power. Existing studies focus on power equipment and telecom failures, such as SCADA, MPLS, DWDM, and other technologies, which are treated separately and not modeled as integrated components of all power system reliability. Second gap was downtime availability linkage. The failure probability is calculated without connecting to mean time to repair. Restoration time and also operation consequences. Power grid in 2005, the DCN, the data connection network, MTTR, was over than 24 hours when the fault happens, creating 77.3% availability. No model existed to quantify this. The third gap was unified probabilistic simulation. Analytical models alone are insufficient for complex multi-layer telecom networks. and it's not combined with the reliability block diagram, and also combined with the Monte Carlo framework. Existed to compare pre-improvement 2025 versus post-improvement in 2026. An integrated probabilistic framework is needed for the links of the telecom network failures and power grid operational impact, downtime analysis and recovery strategy, validating the through both analytical and Monte Carlo methods. Research methodology. We actually described or limited the steps of probabilistic workflow and this methodology into 7 steps. The first one was defining the telecom network topology for the whole, the most of the systems, SCADA and other telecom and control systems. And also we collect component reliability parameters such as mean time between failures and MTTR and failure rates for the Power Grid 2025 operation data. Also, the third methodology was building the reliability block diagram in series and parallel and in hybrid, following the standard IEC 61078. The methodology number 4 was applying probabilistic distribution, exponential the reliability for the time to failure. And also the fifth methodology was calculating analytical reliability metrics by availability and empty mean time to between failures and availability as shown in the equation. Number 6 of the methodology is the run Monte Carlo simulation at 5,000 trails, showing the probabilistic validation where the reliability of Monte Carlo success over number of trails was almost 92%. Number 7 of the methodology was validating and analyzing and recommending the sensitive analysis between 2025 and 2026 and the comparison and also the improvement. In these steps, we actually having multiple steps between the system definition and also the failure and risk management and identification and block diagram, and also probabilistic model and Monte Carlo, and then KPI and improvements. Research log, the methodology follows academic to industrial pipeline mapping thermatical probability functions directly to power grids, real world infrastructure failures. Analytical validation, comparing the reliability analytical versus the reliability Monte Carlo, ensures model accuracy with less than 1% error margin. Data source, Power Grid in 2025 internal operational incident reports more than 170 total faults. The mathematical formulation was actually divided in 7 equations. The reliability function, which shows the probability that the system survive beyond time, exponential model and constant failure rate. And also the second equation was the failure rate, which shows the Power Grid in 2025 number of faults per hours. And also the third equation was the mean time between failures. We calculated that and shows the average operational time between two consecutive failures, which shows almost 82 hours. The equation number 4, availability, which shows the DCN percentage from 77.3% with the MTTR 24-hour per incident to reach almost 99.5% in 2026, with MTTR almost or maybe less than half an hour. Equation in number 5 shows the series system, the reliability series, which shows the system reliability where failure of any component causes system failure, and also the equation parallel, which shows the redundancy model MPLS plus DWDM as a backbone network. In equation number 7, Monte Carlo, it shows the probabilistic estimated based on a number of trails, random sampling with 5,000 trails. Telecom network reliability block diagram showing the series and parallel and hyper architecture with the control center and core router or other L3 network, and also the backbone, which is MPLS and DWDM, and then the substation with gigawatt, and also the power interface between substations. The component and reliability and mean time between failures and MTTR and availability of different block diagrams shown here in the this table, which eventually gives system reliability in analytical calculation with R with the reliability system equals almost 92%. In this slide, we actually having the real operational data analysis. The incident distribution in Power Grid in 2025 shows that almost 28% was caused by DC power, and also 24% of incidents were caused by data center and application, and 20% of DC data connection network, and also 20% for was for the telecom systems, and 8% only for SCADA. As identified root cause analysis, we found that the obsolete telecom and SCADA hardware reaching end of life, and also ineffective change management and configuration errors related to human errors. And also we found that outdated software and firmware lacking security patches, and high utilization leading to critical cooling failures. And eventually we also discovered that the root cause in this kind of matters were related to fiber cuts and IP conflicts and synchronization issues. The number of or maybe the mean time to repair by each technology was shown here in the figure number 2, with different time to each link to each system. In the KPI analysis and availability and mean time between failures and MTTR calculations, we we are having in figure 3 the system availability, the comparison between 2025 and 2026. In DCN and other systems, it shows that in 2026 so far we have reached almost more than 99% after discovering the root cause and treating them, and also the sensitivity of MTTR versus availability is showing in figure 4 with almost 99.4% and only half an hour mean time to repair, comparing to more than 24 hours in 2025. Key sites in these figures was showing reducing DC and MTTR from 24 to half an hour gain, giving us more than 25% point in availability, and achieving through process of optimization without changing any hardware. Monte Carlo simulation and algorithm and validation results. In Monte Carlo, we actually considering inputs with reliability different values, and a trial with 5,000 trials, and also the loop and calculation and results showing in figure number 5 Monte Carlo system success over failure. It gives us a great advance in the system success with 4,600 to success trials and 300 almost 400 system failure. The metric of reliability system in analytical, and if we compare analytical and Monte Carlo, we found that the analytical was almost 92%, and it was exactly as Monte Carlo, and also the failure was the same, which were validated and matched with error less than 1% agreement between these two results. In 2026, the improvement measurable engineering results, we go down from 25 incidents in 2025 to 0 incident so far from the beginning of this year, from 2026 so far, and also from 24 hour as an MTTR in 2025 to less than 30 minutes in 2026 so far. Gives us availability almost 99.9%. The engineering action taken in this situation was having the path redundancy between for the backbone systems and other systems. Also, we were able to focus on technology refreshment for the SCADA and telecom, which actually increased the MTBF, reducing the mean time to repair. Also, predictive maintenance, the early degradation detection, and pre-stages spare parts. The spare parts, we're providing a lot of spare parts, reducing the MTTR from hours to minutes. Also, automated fail over, the sub-second switch over performance, and also the incident black box plus business continuity plans gives us zero operational impact on power grid. And cooling systems upgrade give us thermal incident completely eliminated, and change management and governance enforcement with giving us a configuration caused failure elimination. And this slide, integration of our course methods with the real study in power grid shows that reliability function using the equation reliability of time applied on the system between 2026, 25 and 26 was done in the reliability function. Also the failure rate applied in these figures, showing us the correct usage of them, and also the empty mean time between failures with the number of faults was applied to the real incident data, and showing us the enhancement between the figures from 2025 to compared to 2026. Also in the reliability block diagram in series and parallel and hybrid were used in different technologies such as routers and MPLS and full network model. And Monte Carlo was also used as a number of trails, and other methods were all considered in this study. The course methods are directly applied to power grid operational data, which actually demonstrating complete academic industrial integration and measurable reliability growth. In conclusion, we conclude key findings. The telecom as a critical infrastructure. Telecom networks are the operational nerve system of power grid. Failure in SCADA and other telecom systems directly impairs supervisory control and can be cascaded into grid instability. Also, second key finding was the probabilistic quantification works accurately models the power grid 2025 failure behavior to the mean time between failure almost 82 computed from 170 real faults over 8,706 operation hours. Also, the third one was RBD models, the network.
Mustafa, sorry to
Yes.
interrupt you. I think we have only 5 minutes. After that,
Oh,
the session will
no,
be
no,
closed. How many? This is conclusion. Okay. Yes, yes.
yeah, this is concluded.
Yeah.
Okay. Fourth was the Monte Carlo validations, validates the model, and also the MTTR is dominant lever. And the last key finding was 2026 results, verifying the 8 engineering actions delivered 0 incident and less MTTR, and also higher availability. The recommendation, we conclude with the full path redundancy of the systems and automated failover for fiber, and also pre-stage spares and playbooks, and also technology refreshed program and predictive maintenance and enforced change management discipline. This is the last reference slide. And thank you. And if you have any question and discussion.
Thank you so much, Mr. Fad. It was very interesting project. Yeah, thank you so much for your
Thank you.
presentation. So please attend to the next link I will send right now.